Hello everybody, welcome back to another session of EL 164 online. So today we're going to talk about some different aspects on the PLC that are very important to know and understand. So we're going to be moving right into the next phase here of getting into some the programming aspects and some different features that you can use while programming a PLC. So without any further ado, let's break right into this. So what we're looking at today is Chapter 9. I realize Chapter 9 is still the SLC 500 series, or that 500 series logic. Again, not quite the same as what we're used to. We kind of switched our class over to. Unfortunately, this book doesn't really cover this aspect in the 5000 version very well. It does a good job, a decent job in 500. So we're going to use the 500 as an example, and then I'm going to be breaking into the 5000 series software as we progress through this. So program control. This is a section of the 5000 software where we've got another tab across the top, like we had timers, counters, like we had programming contacts and coils. This is just one more tab across the top called program control. So we're going to be discussing program control today. So, first thing I wanted to talk about before we get too far into this was online editing. I think maybe a few of you may have remembered I mentioned early on in class that we were going to be discussing online editing for the 5000. It has a really nice feature, and I wanted to make sure that you guys were aware of this because it is something that you will be using in the field quite extensively. So the instruction needed to do this is as follows. Okay, here we are. We are looking at online editing. So we're coming down here. We're going to set Start Pending Run Edits. At that point, you can see it put an I and an R here. When you get the I and the R, you're able to come in here and make some adjustments to the program. So as you can see here, I switched that from an XIO to an XIC. Now that I have the I and R, you can see this is replaced. This is what it originally was, and this is what we're going to implement. So when I come over here, we hit the arrow button, we hit OK down here at the bottom of this screen here. At this point, we have implemented a new change here. So as you can see, we're going to kind of go through this again. Come down here, hit Pending Run Edits. At that point, we have an I and an R, indicating that we have changes pending. And when we switch that to an XIC, we're going to come over here, hit this arrow to the right. And that's going to give us the download that information right to the PLC. So online editing, it provides the users with an easy way to implement quick changes without interrupting the machine operations. One of the challenges we have with downloading a program to a PLC is that we need to take it out of run mode, and by doing that sometimes it interrupts the cycle of the machine. Online edits allows us to do some pretty quick, easy changes, nothing that's going to really change the process of the machine much. Maybe add some time to a timer, or maybe flip some contacts around that were acting up a little bit or causing some troubles. But typically nothing too major. If you're going to do a major change, typically that requires offline editing and then downloading that logic at that point. As I mentioned before, we are going to be talking about program control instructions. This is where it's going to be found right here. We got the tab called Program Control. This is where we're going to find some functions, like in this particular case we're looking at first is a JMP and an LBL. A jump, which is JMP, which is when active, when active, the program will jump to the label, and the label is the location the program jumps to. Starting out with the jump instruction. As you can see here, this is what the older version looks like. It's very similar to what we were dealing with today. So this is why this this section of the chapter 9 does seem to make pretty good sense to review. We still have the same JMP and the LBO. So here they're giving us some examples of some older programming style, but it still applies. So if you trigger the jump statement, the program will go from this state to this state. It'll skip over this particular piece of logic. Here they're showing an example of exactly how that particular item works. So you hit the jump label, and when it's on, it's going to skip this rung of logic, and when it's off, it's going to run that rung of logic. So illustrating that. Here's a little more complicated system where they're skipping multiple rungs of logic, which is very doable. So you can skip many rungs of logic. The only key function to this is that you have to make sure that you keep your labels in the same program. You couldn't jump from this program to another subroutine, which we'll be talking about in just a minute. The jump and label need to be in the same program itself. Here they're showing us another aspect of jump label is that you can have more than one jump going to one label. So here we have if input A triggers this jump, it goes here. If input D triggers this jump, it goes here. So both this is some valid logic. It's just, like I said, it's an older format, something that we're not quite accustomed to in the 5,000 range. Here's the jump label. What I did here is I just did a right click on the jump label, and this is the instruction help menu for that. So just getting you guys accustomed to using the jump, the instruction help. This is a really good feature to use. You can just see all the information here available for us. Okay, so here we are. We're looking at the jump label. This jump label that I set up in the RS5000 software. When this guy here comes on, he's turning on that jump label, skipping over these timers. These flasher timers are a very common thing you find in the industry. So as you can see, as I turn that guy off over here, the jump label is no longer being called. And now these timers are flashing back and forth again. So as you can see, ones are normally closed, ones are normally open, and they're flip-flopped. So you got timer 0 turning on this contact, timer 1 turning on this contact or this contact over here. So flipping back and forth, allowing us to turn them on and off. As you can see, as this guy comes on, the jump stop takes place, and then when I hit the stop, when I hit the start, excuse me, it no longer flashes. Here I go, clicking it on, timer stop flashing. Clicking it off, timers will start flashing again. Bam. It starts flashing again. Okay, so that's pretty much it for the jump labels. This is something that's not used a ton in PLC programming. You'll see it used very little. Sometimes it's used to bypass some logic that is no longer used, or maybe a feature on a machine that's going to temporarily be removed. So that's typically where I've seen it in the past, something of those natures. It's never been a real permanent solution. It's usually just a temporary bypass for some logic that's no longer going to be utilized. Next feature we're going to be talking about is subroutine function. Subroutine is essentially a means for us to develop a program with some organization to it. So let's break right into subroutines next here. As you can see here, I did pull up some of the other piece again from the 500s. So all the same terms are used, the JSR, the return and the subroutine. JSR is jump to designated routine. So essentially that's going to be the command that's going to get us to open another routine. The return is going to be the return from that routine, and the subroutine just identifies it as a subroutine. And we'll be breaking into each one of those details here. So here, basically what we're looking at here is the main program. We're calling it the main routine here, the main program rungs. And so what you see here is when a contact closes, they go to jump JSR, or call subroutine is the same thing, jump subroutine. It comes out to another area for ladder logic called the subroutine, and goes to that location, runs all those rungs of logic, gets to the bottom, and returns right at the start of the next rung. Again, the purpose of this is to help organize programs, and we'll be getting right into that detail here in just a second. So here are some of the commands associated with the jump subroutine. We got the JSR, of course, jump to subroutine, the identification of a subroutine, and the return. This is the key piece here. This is really the only piece that we really have to have. The other two pieces of this are kind of to help organize a program a little bit, but typically in industry you very rarely see these two pieces in a program, and I'll illustrate why here in a minute. So here they're calling this a flashing pilot subroutine program, where a good possibility where you need to flash some information or something of that nature, or input flashers. I've seen math, I've seen communications, different things like that, located in a situation where you stuff all that stuff in an area like a subroutine. Works pretty well. Here they're calling this the main program here, and then they're calling this the subroutine here. Where they come in here, they do the jump subroutine to actually control the flashers. So they got the flasher, as we noted here earlier. We got the timer on, timer off, and these guys will just flick back and forth. And here's another illustration of jump to subroutine. So here they've actually got that program incorporated in here. So when you close that contact in the main, it comes out here and calls this subroutine. So when you close this sensor, it makes this JSR, and it allows us to jump to that location. Here's a further illustration of how that exact thing comes through. It comes in here, runs the JSR, jumps out to the subroutine number 3 file, whatever file. In our particular case, we can call it pretty much anything we want, and then it runs the program, hits return, and starts at the very next rung of the main program. And as you can see, you can have multiple different levels here. So you could have main program, a subroutine, calling a subroutine, calling a subroutine, and coming back from there. So it can be rather in depth. Typically in industry, what you'll see is they put all the subroutines under the main and call them from there. This gets a little crazy. You don't want to get too embedded with too many subroutines. It'd get really hairy on how things were accomplished. So here we are. We're looking at basically in the 5,000 range, a series of 4 different commands here. They got the JSR, which is the same as the 500. The JXR, which is something new for us that we're not really going to cover in this class because it's designed more for the high-end programming, like the function blocks or different forms of programming and logic that we're not going to really cover in this class. The return, works the same as it does in 500, and the SBR defines this logic and subroutine, which we'll be discussing that here in just a minute. So to talk about JSRs and returns, we first need to discuss subroutines, and here I want to break into that a little bit further. So a subroutine is a program that is used by the main routine to perform a specific function. Some of the areas where you could use some routines, basically to separate operations of equipment or processes, to help to help maintenance and engineers understand, have a better understanding of the equipment. Essentially, when you have a problem with a machine, it's usually the operator or someone can point you right to the area. And what this does is by putting that area in a subroutine, you're able to troubleshoot, say, 8 or 10 rungs of logic versus 10,000 rungs of logic. So that's a huge plus there. Also, you'll see, as I mentioned before, you have some special operations such as math, or maybe some conversions or whatnot that you'll see in there, like if you got to convert from, say, like hex to decimal or something of that nature, or BCD or something. You got to do some conversions like that to use information. Even some analog conversion stuff you got to kind of manipulate. That's a good place for that. That way, it's all in one area. Communications, configurations, as I mentioned before, this is something that you'll run into from time to time, where you have to do a little bit of manipulation with the configurations to get the communications to work. So that's a great spot for that as well. And then very often you'll find that they'll separate the fault logic, the information that's getting passed on to touchscreens and emails and that kind of stuff. They'll have their own separate subroutine, allowing you to isolate all that information from the rest of it, so you're not ending up with trying to find a fault in 10,000 rungs of logic. So it does help. So what I did is here I put together a little bit of an example. This is something that I've personally experienced, where I had multiple station machines, and what I would do is, when developing and designing those, I would break out a subroutine for each station. In this particular case, as you can see here, I had a load station, and I called the subroutine load station. And station 1, I called it station 1, of course, and 2, and then unload station. So giving me all the isolation for the logic associated with load station, all the logic associated with station 1 and station 2, as well as the unload station. Well, what it does for me is, when I get called over to the machine to say are having a problem with the load station, I already know that I got all the logic associated with load station in one location. So I can go to that one location and start figuring out, watch the station run and see what's acting up. So it definitely helps. So here I kind of broke it down a little bit farther. I said here, so as you can see, the subroutine called load station contains, of course, all logic associated to load station, things like station loaded logic. So if there's some part present logic that I got to deal with, maybe I got to make sure all the clamps are retracted. Maybe there's some of those kind of problems that you run into from time to time. All that information will be stored right here in this subroutine. All the logic, everything associated to that station will be here. So, and just throwing in some more points as well. And then I kind of went through and did the same thing for 1, 2, and the unload station, giving you an understanding of why is this so important. And when you get into industry, you'll find that there will be hundreds of subroutines and machines, and very large machines, and there's a reason for it. They try to do is isolate that information. Some machine builders are better than others. Some programs better than others. So my goal has always been is to try to make everything as logical as possible and isolated, so there's no real issues when it comes to understanding what each state, where to find the information, or where to find the program for each station. So here I'm going to go ahead and show you how to create a new routine. So new routine here, I come in here, I called it new routine, of course, just to keep things simple. So you notice how there's no spaces in there. It has to put the underscore in there. New subroutine. Going to make a ladder diagram. We're going to stick with ladder. We're not going to really go away from any of that. Just kind of showing you some of the different aspects that you have here. So we hit OK. So now at this very moment, I have created a new subroutine. So nothing more difficult than that. So new routine, create a new subroutine. As you can see, I just type that in and then moved along here. So and just keep moving on. And then noting here it is under main task, main program, and then I right-clicked on main program to come up with new routine. So how do we call a subroutine? Okay, in program control, we find the instruction JSR, jumped subroutine, is what the JSR represents. As you can see here, I do have a block called JSR routine. And it's JSR here. So here I'm going to show you how to go about creating a JSR. So here I'm putting a conditional JSR, so I'll put a condition in front of it. So here we got, I grabbed new subroutine as I just created. And then they put some extra parameters in there. We don't need the extra parameters, so I'm going to go ahead and remove all the extra parameters. This is for more advanced programming. Again, we're not getting into too advanced here. This is just getting a basic understanding of how the subroutines work and how we get to those. So now we've got the JSR subroutine. So now we come in here, we can put a contact in here, and I'll throw some input on that, and we've got that covered now. And there we go. So one point that I want to make while we're looking at this is that most of the time in industry, you do not really want to put a contact in front of the JSR. What causes some other issues that I'll be discussing here in a little bit, but the only reason I put a contact in front of it is to illustrate how this item works. So here, what I did is I put a program. I went ahead and opened up the new subroutine program, and I actually I moved those timers to this location. So now I got nothing more than a couple of flashers going on in here in this subroutine. A new subroutine is doing nothing more than flashing back and forth, 1 second at a time. So now we're going to set up this JSR. So we call this. The call of the subroutine is critical for operation. Most applications use the continuous call of the subroutine. So, like I mentioned before, most operations you would not have a contact in front of here. You want to make sure you're calling your subroutine every scan of the program, just so you don't have anything going on with that last state. And we're going to be talking about that in a minute here. That last state can be a problem when it maintains that last state. And only special occasions where applications where you'll see the conditions in front of the JSR. So here we are. We're looking at the operation of this. So we're watching the operation of those timers flash back and forth. So one of the couple points I got to make here is that in this particular case, we have the return in there. I put the return. So we're showing a timer flashing. We're calling it from the main, and we put a return in there, so it's going back to the main and operating as such. So in this case, I took away the return, and as you can see, it's operating exactly the same. No different. So I'm in same routine, new return, routine, new subroutine, and it still works the same way. Still flashes back and forth. So essentially what happens is when the PLC reaches the end of the program, it sees that as a return if it doesn't see a return before that. So when it sees the end here, and you see this end last rung here, at that very moment it returns to main. So, or it returns, I should say, not to main, but to the subroutine it was being called from. So if it was a nested subroutine, it would go back to the nested, the previous subroutine. But in most cases, you're going to be calling from the main. So in that particular case, it would be going back to the main. So here we are with the JSR enabled. We're going to show exactly how this guy works all together. So we got the JSR. We're going we're counting, so that flasher's flashing in the new subroutine. So we're going to go down to the, we're not counting anymore. So we stop counting is what we're illustrating here. Go to this guy, we're not flashing anymore because we're not calling it anymore. Oh, that's the main. I'm clicking back out again. Okay, so now he's back on again. So now we're flashing again. So our timers are flashing back and forth in our new subroutine as we're calling it. So that's pretty much how it's going to work for us. So we'll go back to the main routine here, and we'll see that that's enabled and disabled, that kind of thing. So essentially, what happens when when you disable the jump subroutine? It disables the logic in that block of information, that program block. So those rungs of logic no longer receive they don't get updated anymore. So they're not updating. So as you can see here, this timer just stopped at 666. The other timer stopped at 1000, and it's just not going to count anymore until what? I call this program again, until I switch that contact back on again. When they call this maintaining last state. So, like I said before, the timers don't reset back to 0. We're not scanning the program any further. And when we stop scanning, the logic is no longer being solved. So the information in that program, in that subroutine, is considered to be they call it maintaining last state, which means the outputs in that subroutine will stay on when we remove the inputs or any change of state, it's going to still maintain that same output. So here we're going to illustrate that a little bit. So I'm going to come over here. You can see here I got the guy enabled. See here, and then I'll come in here. I'll turn this contact on here. So now I've got him on. So this coil is on. The timers are flashing along, no problem. All is good. Excuse me. I'm going to turn off this contact now, which is going to turn off the JSR, disabling the JSR. I'm going to go back to the subroutine. What we're going to see is what? We're going to see the timers stopped in mid-stroke. They're no longer timing. And what? That output is still on. I turn this input off, and what? It's still on. It doesn't change state. Why? Because the program is not being updated. I can turn this guy on and off all I want. The state of that's going to stay on because this program's not being scanned. It's not, the PLC is not looking at that information. I come over here, I close this contact and go back, and then once again I have the timer flashing back and forth, and I can turn this contact on and off as needed. Pretty cool, huh? So the subroutine SBR command, it's very rarely used. It's more of something to help you organize your subroutines a little bit. It gives you an indicator at the top of the program that this is a subroutine. So it's the first rung. You'll see it's not terribly important. The program, as you can see, everything we've done up to this point, I have not included the SBR, but you'll be as you'll be seeing here in a minute, it'll be populating that information. As you can see here, I incorporated the SBR command. It typically shows up at the very first part of the first rung. That's typically where that would show up because you want to illustrate that this is the subroutine it's going to, and to indicate that this program is a subroutine. You see it here at the very top left of the program as soon as you open it up. And then as you can see here, I brought it right into the flasher circuit, and I also included the return. So we're going to come from the main, hit this SBR, run the program, and then come out of the return back to the main again. Forcing external I/O addresses and toggle bits. So I'm moving out of the subroutines and all that jump subroutines and return stuff. We're going to move into the next section here. So that's pretty much it in a subroutine. Subroutines are something you're going to find in most all your PLC programs. They're very commonly used. So that's a pretty good tool to use for organizing your programs. So when we're talking about forcing inputs and outputs, this is a good tool to use for troubleshooting issues with programs and validating wiring concerns. But I have to throw a huge warning out there to you guys. This is a area that a lot of people struggle with. It's pretty easy to set up a force into a program. It's even easier to forget about it. So you come into a program, you set up a force, you force an input or an output on, and at that very moment that force is enabled, and you forget about it. And then someday when that input does turn on or turn off when it's supposed to, indicating some kind of fault or maybe some kind of at position kind of thing. And when that does take place, your PLC does not see that, and at that very moment you end up with a machine crash or something gets damaged. Or something gets damaged. One of the very important points, like I mentioned before, is that if you leave a force on, it could do a lot of machine damage. The aspect that I want to make sure everyone's clear on, though, is that even if you turn on a force, at no point should you ever have to worry about hurting an operator or somebody working on the equipment. It should never be a case of safety. Safety is controlled outside the PLC, always. So keep that in mind. The only thing I can think of that could potentially be a possible safety was if you had something in, say, grippers held in the air, some type of gripper or something holding a part in the air, and that part were to drop and land on someone that was inside the machine at that very moment. That would be about my biggest concern. But most of the time, you disable all your outputs. You couldn't open grippers. You can't do anything without all the safeties in place. So essentially, the biggest concern with forces is machine damage. Machine damage is probably the biggest concern because more often than not, I've seen forces get turned on, left on, and machine damage as a result. So here they're kind of showing us how how forces are operated here in the 500 world. Giving us some of the aspects of that. And here I am giving you the same aspect, only in the 5,000 range. So here, as you can see, we're coming into here, looking at this input first. So come in here, I'm going to go force on. You'll see the on come on. It's not actually on at this time yet. I have to come over here. I have to do what? I have to enable the forces. So enable all I/O forces. I click on that. I hit yes for that. At that very moment that I force that input on, now that output turns on. So it's the force overrides what the input card's telling us. So I'm able to force it on. I'm able to force it off. I can and then as you can see here, I can click on and off back and forth pretty easily. Then I go in here and then I go into remove all forces. And at that very moment, the forces are all removed out of the program. Bam, just like so. Pretty easy. Now we're going to look at the outputs. How do we go about force and output? We do the exact same thing. So we force on. Then we come over here, we enable all forces. click on yes there. And at that very moment, we click that guy is on. So now that output is on. I'm going to show you the aspect here of, because that's not highlighted and that's an Allen Bradley thing, I wanted to come over here and show you what's going on there. So it's saying, it's as you can see here, you see forced in that column there. And as I expand on that, you'll see which bit's forced on. It shows you which one's forced. And then that gives you like a red signal there to tell you, right here, to tell you which one's forced. As you can see here, it doesn't really highlight it as being on. And then we come over here, and we turn it, force it off. And we go back to the tags, and you'll see, again, it's highlighted in red here as a 0, and you'll get the same indicator there. So, and just like the inputs, to remove the force, we come up here, we do the forces, remove all forces, and at that very moment, it removes the force. So here they're kind of showing us some of the aspects of 500. This is, they're showing you force on here, enable forces, forces enable. So a lot of this same technology has been used for multiple different platforms of PLC. So it's been around for a long time. Here they're showing us an illustration of how that's done in the old 500 version. Again, looking at the older addressing and whatnot. So. Right, so here they just put a 1 here. Enable forces. And you can see there that'll come on. So at that very moment, that I13 does not no longer works back and forth with this input. It's on all the time. And the same thing with the outputs. I kind of went through that a little bit with the outputs already. So put 2.5. I'm going to force that guy on. And at that point, it shows the forced on. So. As you can see here, that 5 is on right here, so all the time. Forcing outputs off, same thing. Kind of zip through that a little bit. Enable or disable forces while you're monitoring your file offline. So again, you can enable and disable forces offline as well in 5000. And the last point I want to make, just to make sure that you're on board, is that just make sure that when you enable forces, you let other people know in the shop. That way everybody is aware that there's forces keeping something running or overriding a potential problem. So it does get fixed. It's pretty common to have everyone forget that there's a problem after a force has been implemented, and then to have a machine fail because that input was overridden. Safety circuitry. So here we're talking again. I'm going to be very adamant about this one. Is that a PLC is not designed to protect a person from being hurt by the equipment. you might question why is that and all these aspects, but it is very, very critical not to have a PLC controlling the safety aspects of a machine. We have safety devices like curtains and light gate circuits and light curtains and safety mats and all these different devices to monitor operator presence. And all that needs to be monitored by a special safety circuit. The reason for that is that a PLC can be easily manipulated and overridden. As you guys have seen in lab, I mean, we can get in there, we can force things on now, we can force things off, we can do online editing, we can make changes to programs that could really have an impact on how the machine operates. If it was that easy to produce safety aspects of it, to where you're just modifying contacts and forcing things on and off with people around the equipment, it's very easy to make an error in judgment or force something on that shouldn't have been forced on that would cause somebody severe injury, and that's the last thing we want to do. So that's why they remove all safety devices from PLCs. There is a thing called the safety PLC that is out there that actually is a dual controller. It's a pretty high-end PLC, but we're just talking regular PLCs here, and those are not designed to be fail-safe or tamper-proof. So here, sufficient emergency circuits must be able to stop or partially totally up. What they're stating here is basically they need to be hardwired. It's a hardwired circuit. When you hit the E-stop, it removes the power from the PLC, not necessarily from the processor, but from all the outputs. And here's a little bit of illustration of that. So here they've got like an emergency stop, maybe an over travel switch. It's a little on the light side, but you get the idea. If you hit an emergency stop at this point, it's going to override anything you got going on here. You drop this out, that's coming out no matter what. It's at that very moment when that drops out, this drops out. It doesn't allow any input power or output power to the inputs or output cards. Now, it's been my experience that typically, most of the time, they're just removing output power. In very rare cases, they remove the input power. Most of the time, it's just output power because it's output power that creates the motion. It turns on the valves, turns on the motors, turns all these devices on that create motion, and that's what we're trying to avoid. So here's another illustration of the same thing. And here's actually what they're calling a safety PLC. This is a device that is kind of a high-end device that has actually dual processors in there and requires special programming software to program it. So very high-tech device, getting more and more popular all the time. Some unit like this is going to run you around 10 grand or so. So it's a pretty expensive little unit, but it certainly it does solve some problems for us in safety wise. So yeah, here. So they do have ability to perform control functions, but a standard PLC is not initially designed to be fault tolerant and fail safe. So that's kind of what we mentioned before. We just make sure that you're aware that they're very easily manipulated and their design is not fail safe. Whereas safety PLC has redundant microprocessors where they are double checking themselves all the time, making them more fail safe. And here, there's another piece of it. They have internal output circuitry that is used for testing the input circuitry, so they're constantly double checking their inputs and their outputs on a continuous basis. So just some other aspects of the safety PLC here. So redundant backplane circuitry. So again, just dual redundancy. There's a lot of double checks going on there to make sure that the outputs of those safety PLCs are doing what they're supposed to be doing. So here they're just showing another contactor that does the same aspect, but we're just making sure that we're removing power hardware-wise is what they're kind of illustrating here. So we've kind of talked about this a little bit, how the normally closed is fail-safe. Remember we discussed this pretty in depth up to this point. Whereas if you have a normally closed push button to stop a machine, and a hiler runs over that cord at that very moment, that's going to open that circuit, sever that input. It's going to turn that input off, allowing the machine to stop safely, just as if the stop button was pressed.